So to start off with, you almost always will see a stupidly strong base, though it does not have to be stupidly strong. And in fact, as I say that, it can be pretty much any base. It doesn't have to be stupidly strong. Okay? And you will see what is known as our micael donor, okay? Which is really just a fancy way of saying that that structure is acidic and it has resonance stabilization in two ways. So we can create our carbon nucleophile. When we look at our carbon nucleophile, we should immediately say, is that stable? Okay, if it's not stable, we can't remove that hydrogen. How do we remove that hydrogen? We used our strong base. Okay. How do we know it's stable?
Resonance.
We can resonate. Should I ask what you're mumbling over there?
C-Siri?
C-Siri?
Yeah.
I know.
Electronegativity, resonance, induction.
Oh, okay.
C-Siri.
That's what we had to go through yesterday.
Oh, okay. I'll trust you guys. Still not quite sure. But so there's that resonance. I do get a lot of students saying, well, once we have that resonance, how can I continue forwards? Well, we can show resonance going the other direction too. We don't have to go back to our original blue structure to show resonance. Okay. So we have multiple ways to stabilize that carbon enolane. We have blue, purple, and red. Of those three, which one's the most chemically reactive? The negative carbon, so the blue one. It's the most reactive because we're looking at a carbon with a negative as opposed to an oxygen or nitrogen. Okay, so the red and the purple ones are more resonance stabilized and therefore less likely to react. So what we're talking about is the blue one reacting. This is where sometimes you'll see people go, okay, well this is now going to go react with my electrophile. The problem with showing both the purple and the green on the same structure is that you're typically not color coding things, which means you have two sets of arrows doing two different things. It becomes very confusing for someone attempting to do a mechanism. Make sense? Okay. So I will get students saying, well, okay, then I'll just start with that last one, the red one, that doesn't have any arrows on it, and I'll go back to the blue structure. You don't have to go back to the blue structure either, because I can take those electrons, I can move them back down to make that triple bond, and then I can take, and I'm going to redraw that one so I don't have to have such a godforsaken long arrow, have that pi bond come out and react. Okay? People tend to kind of freak out at that and say, well, then that can't possibly result in a product. What we're saying is that that pi bond's electrons are coming out to make a new bond. Those electrons, due to the other arrow here, those electrons are being associated with that bottom carbon. I don't have to draw the blue structure to show that. These arrows force that chemistry to happen. Kind of makes sense? Okay. The other way that we could reference this is if we looked at an alkene, and I drew that, where's the hydrogen go? Which carbon?
The last substituted carbon.
Okay. The end result of that is the hydrogen goes there. There's the positive charge. Did I have to show the resonance structure where the negative charge is on that end? No, I don't. Okay. The arrow pushing is a natural result of. Okay. So we internalize a lot of those kind of meanings. Does that make sense? Okay. Okay. Where does that green arrow now end? You'll note that I kind of left it hanging out there, right? There are two electrophilic sites. It can do direct addition, okay, also known as a 1,2 addition to the carbonyl carbon, or it could do conjugate addition or indirect addition or 1,4 addition to the alkene. Where should it attack?
Conjugate.
Okay, why should it do a conjugate addition?
Oh, I'm sorry, no, direct.
Okay, so now we're hearing it should be direct. So we get a direct versus a conjugate. Which path?
Conjugate.
Direct. Yeah, the
Oh,
carbon.
great. We have a carbon nucleophile. Carbon nucleophiles always do 1,2 direct addition, except when they're Gilman reagents. When they're Gilman reagents, they do 1,4. So the carbon nucleophile is a tricky nucleophile to deal with. Sometimes it does 1,2, sometimes it does 1,4. And a lot of that has to do with the strength of the negative carbon. If we look at a Grignard, it's a fully negative carbon, no choices. There's nothing to stabilize it, it's just a negative carbon. So it is stupidly strong. For sure runs 1,2. In this case, do I have a stupidly strong negative carbon? No, it is resonance stabilized. Not only is it resonance stabilized, it's resonance stabilized twice, because we have 2 resonance pathways, right? Which means that carbon becomes so stable that it forces the 1,4 addition, not the 1,2. Were you just calling out your success there?
Yeah, I told him to put some respect on my name.
Oh my god.
The next part is making sure that we get all of our carbons drawn into our structure. So I'd recommend showing the bond. Okay, and now addressing our carbons. We've got a CH3 followed by 1, 2, 3 carbons to the other direction. There's 1, 2, 3. I've got a carbonyl at the 2. Okay. When those electrons attack, that'll force that internal resonance stabilization. Should place our single bond there. And we'd get a negative charge on that oxygen. What functional group did I create in blue? That's an enolate, and what do we know the enolates do? They tautomerize, the electrons come back down, those go out and pick up a hydrogen from somewhere. Okay. The end result, carbonyl, triple bond nitrogen. Yeah? We good? Okay. That's our micael addition. Okay. Within that, we needed that micael donor because it's the one that's supplying the electrons. Our micael acceptor was our alpha beta unsaturated carbonyl. Okay? Make sense? Okay. Remember this chemistry in the upper right-hand corner? Does that look familiar? And that was our enamine chemistry when we had nitrogen as a nucleophile. Okay, heavily equilibrium dependent. Okay, but we can force it to form the enamine, effectively an enol. Okay, if we remove water in the course of the reaction, so that can help siphon that across to the enamine. Okay, the enamine is really important for conjugate additions. Okay, why? These electrons can come back down. There's a carbon nucleophile. Where it becomes really important has to do with this 1,4. Sorry, not the 1,4 or 1,2. We'll deal with that later. What's really important has to do with its chemistry in forming that nucleophile. Okay, that's the crux of the enamine. Okay, why is it so important? Well, if we switch this down, sorry, I needed the other structure on there. If we start with just a ketone, what is special about this ketone?
It's not symmetrical.
It's not symmetric, which means how many alpha hydrogens are there?
2.
There's 2 potential alpha hydrogens. One of them would result in a more substituted pi bond, which would be known as the thermodynamic enolate. The other one would be the kinetic enolate. If we're using a weak base, or a weak strong base, our oxide bases, we're going to get the thermodynamic enolate. Would that cause problems in our micael additions?
No.
Where's our nucleophile? There, right? What can you tell me about that nucleophile?
It's triply substituted.
It's triply substituted, meaning
There's a lot of electrons there.
there's a lot of steric hindrance there. If we have a sterically hindered nucleophile, what happens to its nucleophilic characteristics? It decreases. So that could become very problematic for running micael additions, okay? Because we don't have a good nucleophile. Why do enamines come in handy? Well, if we go through and look at enamines, okay, we're going to get the same result. Okay, the same issues popping up. A thermodynamic or a kinetic. And what's interesting about the enamine is the thermodynamic doesn't exist. It never forms. If we ran with just a carbonyl, I get the mixture of both, thermo or kinetic. If I want the kinetic, I have to use stupidly strong bases. That's inherently not safe and more dangerous. But if I go through and convert the carbonyl into an enamine, just using an amine, I can now use a weaker base and I get only the kinetic enolate. That's kind of nice. I can reduce the amount of reagents necessary to run the reaction, or the hazards of the reagents to run the reaction, and I get only one result coming out of it, not 2. So why is the thermodynamic not formed?
Does it have to do with the instability, or the less instability of a positive nitrogen as opposed to?
All of those atoms are in the same plane. Okay? Which might sound kind of weird, but they are forced into the same plane due to the resonance through the nitrogen in that carbonyl. Or not the carbonyl, the pi bond, the enamine. What becomes problematic? The hydrogens from one group run into the hydrogens from the other. That steric repulsion disallows the formation of the pi bond there. Because if that pi bond forms, now what happens? Those things get in fight against each other and try to force the structure to rotate, okay? Which it can't do if it's a pi bond. So since the structure can never rotate the p orbitals into alignment to make the pi bond, no pi bond forms there. Even though it would thermodynamically, as far as the pi bond's concerned, be more stable. The other hydrogen can get removed. There's now less steric hindrance. We form the pi bond for the kinetic. Kind of neat. Okay? If we look at reactivity, what would we expect of this structure? Should this be more or less active as a nucleophile?
More.
So we'll draw the nucleophile immediately to the left here. The electrons come down. You said it should be more nucleophilic than if we had the equivalent enolate one. Why?
You're forgetting. Yeah.
Does the nitrogen allow it to be more negative?
What is that nitrogen doing? So the key difference here is which? Nitrogen versus oxygen. What's our difference between nitrogen versus oxygen? Electronegativity. Oxygen is more electronegative, which means what is that oxygen doing on the electrons in this pi bond? Pulling them into the structure, which means that negative charge is getting pulled into the structure, making that enolate less nucleophilic. To act as a nucleophile, those electrons must be shared outwards. So the enamine ends up being a slightly stronger nucleophile than our enolate. Definitely more resonance stabilized. Okay? That extra stabilization helps it with a 1,4. Yes?
How does that work? Because now nitrogen is positive, so shouldn't it be pulling even harder, or is it just?
It's the ability for nitrogen to oscillate back and forth between those charges that really helps out.
Okay.
Yep.
So that positive charge is actually helping it.
Yeah.
Not, okay.
Okay. So cool. Enamines are beneficial beyond just the fact that we can make them and invent a new name for a functional group. Okay. We use them in lab, i.e. the lab that you turned in last week. Last week? No. The lab that you turned in this week. So there's a post-lab question that just asked about that. I just answered that. There you go. Okay. So our conjugate additions, they favor the 1,4. Okay. Water hydrolyzes the imine, so we'll actually take advantage of that because you asked about it. So we'll go ahead and draw out that mechanism. I think I can draw out that mechanism here. It's going to be a bit of a mess. Okay. As is all things with whatever I draw. Hex. Just trying to give myself more space. Ended up kind of shafting myself. I'm going to ignore that half of it. We're really just going to focus on the hydrolysis with our nitrogen. Okay, so hydrolysis, we're really adding H3O plus. The acid helps to catalyze it. Okay, so we could write it as H3O plus, or we could just write it as water. Okay, what happens? And actually, we're going to want to ditch that. We're going to want water in this case. Does the nitrogen want to be positive? So what does it do? Takes electrons. Takes electrons from the closest place it's got, which is that pi bond, which would mean that carbon becomes positive. What does it need to stabilize? Where do I have electrons? Conveniently now drawn on. The oxygen. Okay? And for the sake of simplicity, I don't even want to draw all that. Because I'm not doing anything to it. We get our lone pair on our nitrogen. We'd have oxygen with a positive charge. Does oxygen want to be positive? So what does it do? It could leave. If it leaves, we get the reverse reaction. Okay. So now it's Mustafa's fault instead of Alex's. Way to pass the buck, Alex. Where else could it get electrons from if it doesn't leave? Instead of from the carbons, it could get them from the hydrogens. So we'd have, way to shift around the ring. That was appropriate. We now have our neutral oxygen, we have a neutral nitrogen, and we'd say, well, we're good, we can be done. That has two sp3 atoms, or an sp3 carbon, which we'll reference more importantly as a tetrahedral intermediate. Okay. That is referencing that carbon is a tetrahedral intermediate because it is tetrahedral. Okay. That also gives us a big tip-off as far as the mechanism goes. Since it's an intermediate, we need to keep going. Okay? So what can we do to keep this reaction going? Remember we said acid, typically present. The nitrogen can pick up a hydrogen from our acid. If nitrogen does that, what charge does it become? becomes positively charged. Does nitrogen want to be positive? What does it do? It leaves. Okay. Nitrogen's not the greatest leaving group, so it needs to be forced off. What could force that off? Heat could be something that's helpful. If it's leaving with electrons, we would need something to replace those electrons. So what should we look for nearby? H plus is not electrons, though.
Another water.
We could look for another water. If we did another water, we're going to end up with a hydrate. Ultimately, the simplest answer is we need electrons. Electrons that I conveniently just color-coded red. This would, of course, make our oxygen positively charged. Does the oxygen want to be positively charged? Nope. So what could happen?
Takes electrons from the pi bond.
It could take electrons from the pi bond.
And then could it pop off the hydrogen? Actually, no, that's that.
If we take electrons from the pi bond, all we're doing is drawing a resonance structure. That resonance structure we could have formed if we just had the nitrogen leave. Everybody see that? Okay. So while that's helpful, typically we don't want to be showing that structure. Why not? Given the choice between black versus red, why is the red less stable? Charge? Positive, positive. They're both charged.
Charge on
Less electronegative.
Charge on a less electronegative atom. So it's bad to have a positive charge on a less electronegative atom?
No.
Charged carbon.
No, that's actually a good thing. Why is the red structure bad?
It's less reactive.
Octet.
This goes all the way back to the explicit rules of Lewis structure. Your best Lewis structure must have complete octets. The red structure, that carbon is missing its octet. That makes this structure bad, which means in my mechanism, I need to not be showing how to make it. I can show it to explain why I was allowed to do a maneuver, resonance, okay? But I should not be showing it as an explicit result of a structure or a mechanistic step. Does that make sense? Okay, that is tricky, and I personally feel obnoxious, but those are the rules. Okay? So what could stabilize that oxygen? Okay, we did have the option. You notice I didn't draw a curved arrow on it to draw the red structure, and I'm not going to do that. It could take electrons from the hydrogen. But then something would have to pick up that hydrogen. Was there like a remotely basic atom floating around that just left? Why would the nitrogen be a better source of electrons than the water?
Because N plus is more stable than O plus.
N plus is more stable than O plus. Why?
Because it's less electronegative.
Less electronegative. Okay, so it goes back to all those stinking rules. Okay? There's your full mechanism for the hydrolysis. Okay? Acid tends to be the best way to go through and show that. Okay? We did make some significant modifications from what was drawn up on the slide. Okay, right? Can I delete all that now?
2 seconds.
2 seconds. Okay, we did make some significant modifications from it. Okay, that was because what was shown on the slide was the result of a micael addition, okay, followed by hydrolysis. Okay, so they're saying, oh, we can make this enamine, do a micael addition, and now we have to undo the enamine. Okay, why? We get cleaner results if we go through that intermediate. Okay, kind of makes sense? So it's synthetically valuable to us, though at the same time, it's potentially a little bit more toxic because you're running multiple reactions to do the same thing. Okay. Checks and balances. So can I erase it all now?
Yes, please.
So if we look, the end result that we ran here is we had it all like this. Polite is always nice. Okay. We just didn't show how the enolate tautomerized to the carbonyl. Okay. Make sense? Okay. Conjugate addition reactions. So if we were to try and synthesize this molecule, right, what bonds could we potentially make? You'll notice that we're looking at a larger carbon structure. We've got 2 carbonyls, so this could be a red flag that we're doing conjugate additions, like we just talked about it. Maybe that could make sense. Okay, so let's go through and say
What did
that
you start with to make that?
that's what we're trying to do, is what reagents would we use to make this?
I'm saying what carbon, like the carbon structure that we have?
What carbon structure? This is what we ended with. What did we start with to make this?
And we just want to make up anything.
Yep. With a little bit of caveat, because we could go through and make the argument, well, we started with technically retrosynthesis. Yeah. That would be a dumb question. Okay? Or a dumb, not really a dumb answer, but a dumb question. There's a restriction behind this question that's implied. You need to be doing some kind of conjugate addition.
Is there more than one
Okay?
set of products? Or
Is there more than one possible way to go through and do it? Yes. Okay? So what we should try and think about is, if this is a conjugate addition, trying to split these so we can get a pi bond. So there's our carbonyl. We could do a pi bond there. So our connection is now between the blue carbon and the red carbon. Does that match our conjugate addition dynamics that we've talked about to make that purple bond?
Yeah.
Okay. So the blue one would be doing, instead of a 1-2, it would do
1,4.
1-4. Where's the 4 position?
Where the purple bond is?
at the end of the end.
It's at the end. Oxygen 1, 2, 3. That would be doing a 1-3 addition, which we haven't addressed. So that probably doesn't make sense as a way to pattern that one out. Okay? What about if I made the pi bond here?
That'd work. That's 1, 2, 3, 4.
Okay? So now that purple bond is the new one I'm making. Everybody see that? Okay? So now we break down 1, 2, 3, 4. We good? Okay. So one option is we start with this one. Sorry, I know I drew that ugly. And that one. Yeah? Okay. Those examples we just walked through assumed that the rightmost carbonyl was what? The micael. Trying to fish for those stupid terms, I know. Acceptor, because it accepted electrons from our nucleophilic structure. Okay? Could we have done it the other way? Okay? There's my 1, 2, 3, 4, right? Why would that not work?
Because then it's a 1, 3 addition.
It's connecting a 1, 3. Good.
Is it possible to put the pi bond on the outside?
Yep. So the other way to do it would potentially go this direction if we count this out. 1, 2, 3, 4. Everybody see that? Okay. Can I have the pi bond on the outside? Yes, absolutely. That is fair game. Which means I could have also done this reaction. With either of these are not technically micael. And so I misspoke when I called them micaels. Why are they not micaels? And it's the blue structures that make them not micaels.
You don't have an enamine.
For it to be a micael, we would need to have that enolate structure where it was doubly resonance stabilized. Okay? These are just enolates. The problem with enolates is they do both 1, 2, and 1, 4. Okay? So these wouldn't work under Michael conditions as shown. How could I make them Michael?
Instead of breaking it apart into two, let's go back and choose one of those carbonyls and turn it into a nitrogen. So, like, no, not, or.
I'm doing it for you. Shh. We could now take it to an enamine. That nitrogen does not want to be positive, so how does it shift its electrons around? And we get rid of the enamine. Now is a good Michael donor. The enamine could go through and react, at the 4 position. Make sense? We could have formed the enamine with this guy as well. Everybody understand that? That would make them both Michael. So let's get rid of Michael because Michael can be confusing and just run it as kind of a conjugate addition. Okay, so let's clean it up now because we have proven that we can make them. Sorry, you started to take a picture. We've proven that we can make them Michael reactions. Now let's not worry about the Michael reaction because the Michael addition part is just making it an enamine and then removing the enamine. We put it on, do the Michael addition, and we take it off. Yeah? So now let's just worry about the overall chemistry. Is one of these pathways better than the other? Probably. Good answer. What do you think? The blue structure in both cases needs to act as what? The nucleophile. It needs to donate electrons because it's what's attacking the 4 position, our electrophilic site. Okay? So the red structures are both electrophiles. And the blue structures are nucleophiles. Okay? The electrophiles started as electrophiles. Right? We don't have to do anything to those. They're already electrophilic. Are the nucleophiles nucleophilic? No. We have to make them nucleophilic by doing what? Which hydrogen? Acidic hydrogen, that's the word I was fishing for. An alpha hydrogen. If we take a look at the alpha hydrogens, there's 2 alpha hydrogens there. Actually, no, there's 4 alpha hydrogens. They're all the same. So I don't actually have 4. I really only have 1 that is repeated 4 times. Okay? 1 alpha hydrogen. What happens with the other structure?
It has 2.
Well, there's 5, but then those are again repeated just like we had with the last one. And if I did a good job of color coding, which I didn't, we have green versus purple. And green versus purple is really asking, I know that was super vague.
You're asking which one of them is the most acidic?
It's not more acidic because they're both the same acidity.
Oh, then why not both? 2 products. So you want to make a selective as opposed to a non-selective?
Thermodynamic versus kinetic. Okay? That thermodynamic versus kinetic adds a layer of complexity behind that synthesis. Do we want to worry about that complexity? So what does that mean? This was a crappy answer. That's the better one. Okay? Does that make sense? So we can still control the kinetics and thermodynamics. We have the ability to do so. We have the ability to control a lot of things. That doesn't mean we want to have to control them. Okay? Robinson annulation, okay, which is really just a fancy way of saying we're going to do all of this chemistry all at the same time in one giant pot and hope nobody gets mad at us. Okay? Why did we get a name attached to it? I think we get a name attached to it because we're doing a ridiculous amount of chemistry in one reaction flask. We just mix in some stuff, we stir it around for a little bit, and ta-da, I get a product. Like, well, how the hell did all of that happen? Okay? So that's why I would argue Robinson gets to attach his name to it. It's really just a long, drawn-out mechanism. But if we start with it, what happens? We have sodium hydroxide. Sodium hydroxide is a base, or a nucleophile. If it acted as a nucleophile, under most of these circumstances, what would happen? What would we form if it attacked here? Close. Not a hemiacetal.
Hydrate.
A hydrate. Okay? Because we're adding hydrogens. It's not an alcohol that's being added. What if it attacked here? It's the same answer.
Yeah.
Hydrate. It would also form a hydrate. Or there,
Hydrate.
it would also form a hydrate. And what do we know about the hydrates?
They are equilibrium dependent.
Unstable, and they revert backwards. Okay, so they are equilibrium dependent, but they are largely not your primary product. Okay? It could have attacked here. Okay, in a 1,4 type nucleophile addition. Okay, that is a possibility. Okay, what else could it have done? It's a strong base. Is there something remotely acidic?
Yes.
Yep. We have an alpha hydrogen in that di-resonance possibility, which means the base can come in, remove that hydrogen. I'm not showing this full mechanism, by the way. So I'm going to draw and erase and draw and erase a whole bunch. So it comes in, removes that hydrogen, shuttling the electrons to that carbon, which means our carbon is now negatively charged. I could show resonance. Ta-da! Okay. I could also show resonance. Ta-da! That's why that can form. Now that it's formed, what can it do? That is now a nucleophile. It can attack the 1,4 position. Okay, this one I have to draw, unfortunately. So helpful to count our carbons, putting a nice solid dot. 1, 2, 3, 4. 1, 2. Scheiße. 4. 1, 2, 3. Nope. That's why it's helpful to pass first grade. That is kind of insulting. Mildly, right? For those of you counting, I was the one that miscounted.
You make math jokes. What are they jokes?
They're pretty serious, unfortunately. Okay, what have we formed?
Enolate.
We have an enolate. Are enolates stable?
Nope.
No, what do they do? Tautomerize to form the ketone. Okay? What reaction did we just run?
Michael.
That was the micael addition. Okay? Now what can happen? We're still in a basic environment. Okay, so we could still remove acidic hydrogens. Okay? For those of you counting, because I forgot to mention it, that purple hydrogen way back up at the starting material now, you see it up there? Was that also acidic? Yeah. Could that have been deprotonated and become a nucleophile?
Yes.
Yes. Is it as likely to?
No.
Why not?
Because it's less. It's not doubly resonant.
Not doubly resonant, so it's less acidic. Okay? But it is possible, which is why we could run into all sorts of side reactions. Okay? So now the question is, well, what is acidic left over? We don't have the double resonance anymore. There's no hydrogens there. I do have alpha hydrogens located here, here, here. I'm drawing it on the wrong structure. God damn it. It's like something just does not look right here. I can't put a hydrogen there. Here. And here.
Kinetic versus thermodynamic.
We could try kinetic versus thermodynamic. Okay? And ultimately what we do is we should test the removal of each of those. Each of those is going to make a nucleophile, which could then react with an electrophile. Right?
Yeah.
An electrophile would be a carbonyl. Is there a carbonyl nearby? Yeah, there's 3 carbonyls nearby, which means there are
A whole bunch of different products.
3 possible electrophiles. We've got 4 nucleophiles, 3 electrophiles. Yay! This means going through and testing each of those paths and seeing what you result in. Okay? This could be good reasoning for why we attach a name to it. Because somebody went through and did that. Except I'm going to argue they probably didn't. They probably did what's shown up top. They threw a bunch of stuff together, assuming something was going to happen, and then this weird thing fell out. Like, well, how did that happen? Okay? If we look at that versus here, what happened?
That alpha hydrogen, the light blue one, comes off. And
The light blue formed our nucleophile, and it attacked that carbonyl in an aldol reaction. Once you know what the answer is, the mechanism becomes pretty easy. You don't have to do all this other nonsense. Okay? But if you don't know that final answer, going through and showing all those products, you'll find there's a whole bunch of products, some of which make absolutely no sense. Why? Let's take that green one and attach it to there. Okay?
it's not.
The result of that is this, with a bunch of other stuff on it that I don't feel like showing right now. It's 2 4-membered rings next to each other.
That sounds like an explosion.
That sounds like an explosion. That is not particularly stable. So what does that mean about the likelihood of that reaction happening? Not very likely. Okay? But if you've seen all of those possibilities, by drawing them out, you are more likely to be able to not draw that when it gets to the exam. Does that make sense? Okay? Which is going to bring in the next kind of part with this. Notice in that connection, it's going to be very easy to lose track of pieces. So what could we do to help simplify that? If I want to connect those 2 pieces, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When I connected that, I connected 1 to 8. 1 is also connected to 2 and 3. 3 is connected to 8, 9, 10. Kind of see what I'm doing?
Now you can draw the rest of it on there.
3, there's that methyl. There's 4. There's 5. There's 6. There's 7. 6 has the double bond.
So those
8 has the negative charged oxygen. 2 has the carbonyl. And yeah, it looks awful and ugly. Thankfully, you don't have to grade it. Okay? But at least that way you've got it numerically aligned so that you know where all the pieces are. Because if you don't put the numbers on, guess who does put those numbers on? The person that has to grade it. Okay? Because it is virtually impossible to track where all those pieces are. Okay? Remember, with these, each of these structures could be picked up, turned, flipped, and rotated, which means the alignment doesn't look perfect, which means you can't just transfer the pieces directly across. Kind of, sort of? Okay. So that's the Robinson. It's fancy because you did a micael addition and an aldol condensation all in one giant pot. Okay? And we all love one pot. We'll just skip that. Chapter 19. If we go through and look at this and we try to react these 2 molecules, we're not going to get a reaction. Why not?
because they're both the same charge, like charges repel.
Okay? So what you have to do is to look at those reagents and be like, they're both positively charged. The reactivity on these says they don't react. So if I drew out a bunch of random reagents and said these things react, okay, what do you need to find?
What's reactive?
What's reactive? Negative and positive. Not when did we talk about this reaction? Because I guarantee you, I will ask questions. You will see questions, let's put it that way. You will see questions where we haven't talked about the chemistry at all. Okay? But what we have talked about is those balance of charges, and if you can identify those charges, you can do the reaction. If instead you memorize the reagents, you're going to see that reaction and be like, what the hell is this? Okay? So look for those charges because those charges are helpful. Okay? If I still want these two pieces to connect, what do I need to find?
A negative.
I would need to make a nucleophile. How could I make a nucleophile? One of these needs electrons somehow.
Could you make that one a Grignard?
That one a Grignard. I'm going to assume you meant this one into a Grignard
That one.
by adding magnesium.
I like that.
Awesome. You've now made that carbon negatively charged. You've changed the charge on the atom through running a chemical reaction. We talked about this very briefly. It's known as the, I'm not even sure how to describe it. Umpalung. It's an umpalung reaction because you've changed the charge. Okay? How about the other one? Could you have made the other one a negative?
Yes.
Yes.
You could use a base.
We could use a base. What is the base going to do? The
Pull off.
base would remove the hydrogen. It's not keeping the chemistry at those positions, okay? But it is at least changing one from a negative to a positive. Okay? Does that make sense? So I would argue with the way I framed the question that Grignard was the better call, but we could make either of these into nucleophiles. We know how to do that. Yes?
Is that like can you make these two carbons react as opposed to can you make these two things react?
Yeah, that's how you could potentially change that wording around. Yeah. So see, I didn't make it up. It's apparently a real thing. German word, there you go. Polarity reversal. Okay. If you trust the slides, okay, it's an Umpalung reaction. Okay. We didn't have to do it as a Grignard. We could have done it as a Wittig. There's tons of different ways we could have done it. Okay. But the idea is recognizing that you're trying to change the charge so that you can make a connection between structures. Why would that be useful? When would that be useful? When we want to synthesize something and we see that we have these two pieces and we need to connect them, we can start to recognize how we can change those charges around to build larger structures. Okay? So if we can first identify those charge sites, we can then start to simplify what reagents we could potentially use to connect them. Make sense? Okay? And that's why this is showing up in the synthesis chapter. Okay? So we could do it with Grignards, you could do it with Wittigs. That's ultimately all this says, so I don't really care. Okay? Then Carty goes through and summarizes carbon-carbon bonds. We've done a whole bunch of carbon-carbon bonds. Okay? The nitrile attacking as a nucleophile. Alkenes with Wittigs. Okay? Hydroxyl carbons. Okay? Doing aldols. All he's trying to do is summarize how we can make a bunch of different carbon structures longer or attached to each other. We've already done this a whole bunch. It's just a way to summarize it. Why would it be useful to have that summarized?
So we can study it.
You could do it as a potential study tool as I need to memorize these reagents. And it is useful for that. When would it be useful?
For synthesis questions.
For synthesis questions. So if you see a synthesis question, finding tables of reagents is a good idea. Right? Because you probably don't have them all memorized. So if you can find out basic patterns of functional groups, you now know how to sort through some tables to come up with potential ways to shift through it. Those tables are at the back of our textbook. They're at the back of any good organic chemistry textbook. We'll have tables of reagents. Okay? Everybody formats them slightly differently, but they're useful. You should take advantage of them. These summaries also show up at the end of each chapter. Okay? I'm not positive that other textbook does this, but I know Carty does. He'll actually reference the section chapter-wise where that chemistry came from. So if you're like, I have no idea what the hell this is, you could go look it up. Okay? Or you could be like, I have no idea what the hell this is. Did we talk about that chapter yet? Nope, probably shouldn't use it. Okay? Yeah? Ah, damn it, I should have known that. Okay? Those are your two kind of flips on that. Make sense? Okay, so there's more of that table. This chapter also talks about selective reactions. Okay? We've seen selective reactions pop up before. If I want to run a substitution reaction. Okay, so let's go through. I'm erasing probably something that I'm about to just redraw, but whatever. if I want to do a substitution, what reagent should I add to complete this substitution? So, what's different?
You added an OH.
Okay? So, chemistry did not change positions, right? Which is kind of a red flag that we're probably looking at a substitution, maybe an acid-base reaction. Okay? So, yeah, we're probably looking at substitution here. Well, what did I substitute? Chlorine became OH. Minimally, what do I know has to be added? I have to add OH. Problem with adding OH is that that's not neutral, right? Come in as OH minus. Okay? What's the problem with OH minus? And then officially, yes, we'd have to make it super neutral. Na plus.
Both a base and
Hydroxide is both a base and a nucleophile. In this reaction or this setup, would I expect it to act as a base? Why not?
because you have a good leaving group, so you could get an elimination, but ultimately
If it acts as a nucleophile, what reaction?
a substitution.
What mechanism?
So SN2.
SN2 because
It's simultaneous because it's good
Primary
nucleophile.
substrate.
strong nucleophile. If it acts as a base, we'd be doing
And E2.
E2. Okay, Y2.
Because it's going to.
Same reason as it was SN2. It's a strong base. Okay. Looking at our substrate, what is it going to favor? Favors SN2 because a primary substrate favors SN2. E2 needs tertiary. Okay? So that reagent is now selective as a nucleophile, not as a base. Okay? You had to be able to reason through some of those pieces when you processed that. Does that make sense? Okay. If we go through and look at our reactions up here, why is NaCl selective for substitution?
Because it can't be a base.
Chloride can't act as a base. That means chloride can only act as a nucleophile. And what's the only reaction that has a nucleophile? Substitution. Right? We move to this one, NaOT butoxide. This is a little bit over the top, but it's not too bad.
Weak base?
Okay? It's negatively charged, so it's not weak. It's strong. Why is it a strong base and not a nucleophile?
Bulky?
It's bulky. That size makes it very difficult for that reagent to act as a nucleophile, which means it can only act as a base. What reactions use bases?
Elimination?
Elimination. So that reagent now becomes selective for an elimination reaction. Okay? So you've seen it in our substitution reactions from first semester and from our very first unit. Okay? Most of the reagents we talk about are designed to be selective. Sometimes they aren't. Okay? But that's what you need to be thinking about when running through a substitution or running through a synthesis. Making sure that the reagents you pick go with one path and only one path. Most of the syntheses we've dealt with are relatively simple structures where we're only maintaining one change to the structure. Okay? And all of the chemistry is centralized and we now make that chemistry move somewhere else. But what if we have starting materials where there's multiple sites of chemistry? For instance, if I add another pi bond, okay, could that affect those other reagents?
Yeah.
Maybe. We now have to make sure that the reagents we're adding only react where we want them to. That's the selectivity behind it. Okay? That is a challenging thing to talk about in class because every structure is going to be unique and different. But what you need to start to do is being like, well, I remembered when we talked about our alkenes, and I remembered when we talked about our carbonyls, and that when they reacted, there's only a few cases where they overlap. Carbonyls tend to act as electrophiles. Alkenes tend to act as nucleophiles. they're in separate categories as far as reactivity. So they probably won't interfere with each other. Unless, of course,
You add a certain reagent.
I add a certain reagent, like hydrogen. What if I reduce, okay, the addition of hydrogen to a pi bond? Okay? They're both pi bonds. When I add hydrogen, do I want it to add to both or just to one? That's going to depend on the reaction I'm trying to run, which means in those cases, I now need reagents that will target those things in particular. Does that make sense? Okay. Yeah, I don't want to look at that. Yeah, this is the slide I thought we were going to get at. So our hydrogen. If we just had a pi bond, hydrogen and a metal catalyst, okay, we add hydrogen across the pi bond. What happens to the pi bond? It goes away. Fantastic. Not selective. Okay? Any pi bond, that can be forced to react. Okay? The conditions of that forcing become questionable and nuanced, and I don't want you to deal with that nuance. So don't stress about that. But realize that if you have hydrogen and a metal, and that's it, just reduce. Reduce what? Any pi bond. Okay? There were other hydrogen reagents we could have done. We could have done hydrogen and a poisoned metal. Okay, well, the poisoned metal now doesn't react with alkenes, but it reacts with alkynes. Okay? Similar process. Or we could do sodium and ammonia. Okay, so those were kind of our old school reducing agents. When we move in with the polar pi bond, they have slightly different chemistry. We can try and take advantage of that difference in chemistry to target them with different reagents. Okay? This is where you get the Wolff-Kitchener reduction. Okay? As a name, don't stress about the names. Okay? But there's a Wolff-Kitchener reduction. Okay? What's interesting about that reduction? What did we do to the carbonyl?
Completely obliterated.
Completely gone. Kind of like what we did with our other pi bond structure. Could we have reacted the carbonyl in such a way where we didn't get rid of it altogether?
Yes.
With what reagent? Somebody else.
PCC.
That doesn't get rid of the carbonyl, that adds more oxygens. That's doing the opposite. How could we reduce the carbonyl without getting rid of the oxygen?
By adding an alcohol.
We want to end at an alcohol, which might be a good tip-off.
So you add
Carbonyl to an alcohol.
acetal something? What do you add for that?
Okay? So sometimes structures can be helpful, right? So let's take a look at a structure. If we take this structure and we turn it into an alcohol, what did I have to add to this? Not O.
NABH4.
I needed to add an H there, right? What charge did that H have to be to react with that carbon?
Negative.
Negatively charged. Where do I find negative hydrogen?
NABH4.
Sodium borohydride, or
H2 with a metal?
that's the top one, and that would potentially work. That's not where I was going. Okay? Lithium aluminum hydride. Okay, would also do that. Okay? In this case, it completely ejects the alcohol or the oxygen, no longer attached to the structure. Okay? Clemenson. Okay? Clemenson reaction, you take zinc and mercury in the presence of acid and water, and you get this structure. This one I find really, really interesting. What charge is that carbon? Positive, which means what charge would the hydrogens be that you added to this? You would assume they're negative. They're positive. The oxygen reacts with the zinc in such a way that the electrons in that bond go towards the carbon, not towards the oxygen. And it has to do with the oxidation states of our zinc and mercury. Neat little mechanism. Take a look at the book. I'm not going to show it. Okay? But I think it's kind of cool. Yes?
You did that with the electronegativity. The both metals will electronegativity, so they're going to get the electrons into the structure, right?
If they become charged at the end, yeah. Okay? Last one, I don't remember its name. Anybody remember? All I remember is Rainy. Okay? But it's not just the Rainy nickel, because guess what Rainy nickel does? That's nickel and hydrogen. It'll also do our alkenes. If I don't want it to attack the alkene, that's where I throw in the dithiol. What's the dithiol doing? It's actually not protecting it. It's reacting with the carbonyl to make it react with the Raney nickel better. Okay? So it's forming an acetal-like structure. Why would I choose one reagent over another? Well, it comes down to the rest of the structure. If I take a look at the Wolff-Kitchener reduction, what am I adding here? What's the nitrogen acting as?
An acid, right?
It's a source of electrons that attacks the carbonyl to form an imine. It's a nucleophile. Why would that be problematic if somewhere else in my structure I had another electrophile? Then that's probably a bad reaction to run because the nitrogen will attack. What if there's an acid somewhere else in my structure? What is the acid going to do to the KOH? It's going to kill it. Okay? So each of these reagents have slightly different conditions. Those slightly different conditions aren't designed to necessarily affect the carbonyl transfer. They're designed to not affect something else in the structure. Okay? So if we take a look at the Wolff-Kitchener, what things are going to be problematic? We have a nucleophile and we have a base. How about in the Clemenson? What's our reactive thing? We have an acid. How about in the Wolff-Kitchener? Or not the Wolff, the other one, the bottom one? Okay, we have a nucleophile, we also have an acid. We also have just straight up hydrogen addition. Okay? So depending on what else is in our structure, I'm going to want to select one of these reagents over another. Okay? That is a challenging concept to deal with. Does that make sense? And that's really just going to come with a little bit of practice looking at structures and evaluating them. Ultimately looking for what? Positives and negatives. Okay? Okay. Yeah, we're not going to worry about that. But we'll look at our oxidation. With our oxidation reagents, it's a little bit simpler. We're only going to deal with 2. Okay? When we move into lab, I'll give you 3. You don't have to worry about it for the test, though. Okay? But for lecture, there's 2 oxidizing reagents. Chromic acid and pyridinium chlorochromate. Okay? Chromic acid is a bit irritating. What are all those equals supposed to be representing?
They're all chromic acid?
They are all chromic acid, meaning we could write any one of those and they're all referring to the exact same thing.
Do I need a chromic acid?
With H2SO4 and the commas are included in that one. Okay? And I think there's a couple other ways to go through and do it. Okay? So you've got to be careful with the chromic acid one because there's a variety of ways to show it. Okay? All of which mean the same thing. Okay? It is a stupidly strong oxidizing agent. Okay? So if there are hydrogens to remove, it will remove them and replace them with oxygen. Okay, so let's take a look at that primary alcohol. Where's the reactive carbon?
Carbon 1.
The one attached to the alcohol.
The one attached to the alcohol. Are there hydrogens? Yes. Which means chromic acid is now going to come through and it's going to replace those hydrogens with oxygens. Ta-da, we're done. Is that what it shows as the final answer? No? What functional group do I have in red? A hydrate. And what does a hydrate do?
You have a trihydrate.
Just in red. What do hydrates do?
Decompose into or
They
polymerize.
radically exchange back into
Water and
the carbonyl. Are you sure those answers weren't the same?
yeah.
Okay. Yeah, they are the same now. Okay. The hydrate form switches to carbonyls. So when we go through and evaluate, all that's happening is if you have hydrogens connected where the oxygen is located or your alcohol is, change them into oxygens. That's it. Then what do you also kind of technically have to remember?
Take that water.
That chemistry that we talked about in chapter 18, where we talked about hydrates and acetals and hemiacetals. Okay? So if you have that content to build, it's an easier reaction to deal with. If you don't have that content to build, you have to memorize a couple extra steps. Kind of, sort of? Okay. So that's chromic acid. PCC, pyridinium chlorochromate, that's why it's PCC. I reference is politically correct, because politically correct humor, boring, isn't as strong or active as, regular humor, right? Okay, so it's a little bit less good. So what does that mean? If we have politically correct chromic acid,
It's like a swim.
it's not as strong.
Hard to say.
It won't oxidize as much. Okay, it'll still oxidize. That line happens to be with our primary alcohols. It'll go to aldehydes and then stop. Okay? That's your big difference. PCC, make aldehydes. Everything else, oxidize the crap. Make sense? Okay. I think PCC is kind of fun. Let's see, to actually keep it in the slides, is the difference between these. Okay. PCC, pyridinium chlorochromate. The pyridinium chloro is actually the whole other piece. Guess what the chromate is?
Bromate.
It's the exact same thing in chromic acid. So why, if it still has chromic acid in it, does it not work as much?
Probably.
Okay.
Pyridinium chloro.
It has to do something with that pyridinium chloro. Okay, and really what this difference is the pyridinium chloro versus water. Okay? Here's pyridinium. The chloro is just a counterion. If we look at just chromic acid, it's in the presence of water. Okay? And so what happens under both cases is the chromic acid reacts to this neat little mechanism, and it ends with the aldehyde. Okay? What's the issue with the aldehyde if there's water present? What does the water do?
The chromate recharges off of water.
It has to do with the aldehyde itself.
Attacks.
The water attacks.
Yeah.
If the water attacks, what does it make? Positive, negative, we don't like that, so how do we fix that?
Get rid of ammonia.
What did it make?
Another alcohol.
It made a hydrate. And in particular, what functional group did it make? An alcohol. What does chromic acid react with? Alcohols. Now the reaction can continue. Okay? Because I now have the species that can attack chromic acid. In PCC, it's pyridinium. There's no water. If there's no water, I stop at the aldehyde. No water means no hydrate. No hydrate, no continuing of the reaction. So literally the only difference between PCC and chromic acid is the presence of water, which is easily tested. You take a reaction with PCC,
Add some water.
add some water. What happens?
Same thing.
Turns into the carboxylic acid. It oxidizes all the way down. Okay? So it's hinging literally just on the solvent. In one case, the solvent isn't nucleophilic enough to generate an alcohol. The other case, it is. Once we have the alcohol, the oxidation occurs. That's kind of neat. Okay? But that's our difference between those. It's the existence of that hydrate. Okay? So within our summary, here's all of our oxidation as summary. Try to put on one big chart. I know it looks kind of confusing, but if we start, we have an alcohol with 3 R groups, and now chromic acid. Any one of those reagent sequences. Yeah? If the R groups are 1 carbon and 2 hydrogens, what kind of alcohol did we start with? primary, which means we end with the carboxylic acid. If we have 2 carbons in our R group, we have a secondary, which means we get the ketone. If we have all R groups, there's no hydrogen to remove and we get no reaction. That could show up as a no reaction. It could also just show up as the starting alcohol redrawn. Okay? If we go through and look at PCC, same system, but it's now going in reverse. Primary's at the bottom, secondary, and then tertiary. Make sense? Questions? Okay. The rest of this chapter talks a lot about protecting groups. Protecting groups are useful things, but as we talked about earlier, why are protecting groups typically frowned upon?
Green chemistry.
Green chemistry. You're putting something on the structure as a chemical reaction so that you can do something so that you can then take that protecting group off. That's adding a lot more reactions to it, which increases safety risk. It also increases waste production. So in general, for a synthesis, we want to avoid protecting groups as much as possible. Sometimes there's nothing you can do about it, and you got to use them. Okay? In those cases, what would you do?
Minimize as many as you can.
You could minimize as many, yeah. But now you have to use a protecting group. What do?
Use it.
There's lists of them. There's just tables of protecting groups.
Oh, then we found the one that's then.
You would just go to your tables of protecting groups and pick one. Which is also one of the reasons why I'd be like, well, we shouldn't really lecture on this, because all I'm going to tell you to do is just look up tables of them. Yeah, it's kind of dumb. Right? But there are some kind of neat things that you could do with it. Some of them you've already seen. Williamson ether. You've got a couple different ether reagents. Okay. Note the thing that's interesting is the steps being used to add and remove them. In most cases, the steps being used are really just simple acid-base steps. Okay? So to put a protecting group on, we want to be able to put it on, but then we also need to be able to take it off. The easiest way to do that is acid-base. Just noticed this one is not used very often because this is chloromethyl ether. It is a nasty carcinogen, and it's on the DEA watch list. Okay. So most people don't use that one. Okay. There is also cases where you will see these large weird groups show up. Okay. These large weird groups are, again, partly to deal with solubility. Notice that we've got the kind of diether structure happening in there that we also had over here with our nasty chloromethyl. We just added some other stuff to it. Why? Because that probably took it off the DEA watch list. Okay? But that structure becomes so complicated to name that you see the abbreviations DHP, TBDMS. Okay, so if you see a structure that has those kind of string of letters attached, really what they're saying is they're adding or removing protecting groups. Okay, and I am shocked, as that is literally the end. We've